Part 2, planar graphs. One of the fundamental questions in computing relates to something called the traveling salesman problem. Suppose there are n cities that you as a salesman must visit. You know how far apart any two cities are. For example, Palo Alto, California might be 35 kilometers from Oxford, which is 12 feet from Cambridge, Massachusetts, which is 100 angstroms from Palo Alto. The traveling salesman problem is the task of finding the shortest route that will take you through all of the cities. Naturally, you could just look at all possible trajectories, all n factorial of them, I suppose, but that would take a really long time. Computer scientists are interested in whether or not it's possible to somehow quickly find the optimal route. Can you do this quickly? Which generally means in a number of steps that's a polynomial in the size of the input, the graph with all of its data. This problem is in a precise way equivalent to the satisfiability question, which is a problem that we discussed in the propositional logic unit. While this graph contains more information than what we've been considering, it still is an example of a complete graph. A complete graph is a graph in which every pair of vertices is joined by an edge, and we denote the complete graph on n vertices by k sub n. This is the complete graph on 3 nodes, and this is the complete graph on 4 nodes. Note that there is no node right there in the center that just happens to be where 2 of the edges cross. A similar problem occurs when you're dealing with electrical circuitry. In the propositional logic unit, we consider this circuit, which computes something. But here we have some lines crossing, and maybe you could have a short circuit of some type. Of course, we could eliminate that by simply switching the location of 2 of the inputs, but then we have a related circuit where we would have problems. It's unclear if we'll ever be able to straighten out all the circuits that we need to so that lines aren't crossing. You want to redraw a graph so that the same pairs of vertices are connected by edges, but no 2 edges cross, or as few as possible, except, of course, at nodes. No 2 edges cross in the middle. Can K4, the complete graph on 4 vertices, be drawn so that no 2 edges cross? This is quiz 4. You can say yes, you can say no, or maybe it's an NP-complete problem. And the answer is yes. Here's one way. You still have each pair of vertices joined by an edge. Here's another way. Here again, every pair of nodes is connected with an edge. And because of that, these 2 graphs are actually isomorphic, as we say. Let's explore this concept. Let's look at all the possible graphs that are essentially the same. If you have 1 vertex, there's only 1 graph you can have. If you have 2 vertices, there are 2 graphs. You can have 2 nodes that are not connected by an edge, or 2 nodes that are connected by an edge, and these are clearly different graphs. They're non-isomorphic graphs. If there are 3 nodes, there are 5 graphs you can make that are essentially different. You could have 3 nodes with no edges, or 3 nodes with 1 edge connecting a pair of nodes. Now we could give these nodes labels and draw what seem like 2 different graphs. Say this is node 1, node 2, and node Fred, and this might be node alpha, node beta, and node 3, but there's clearly a correspondence between these nodes, which somehow preserves the structure of the graph. That would be an isomorphism. So, strictly speaking, we could draw 3 edges. We could draw an edge between Fred and 1, but that again will be the same as this graph, essentially, even though we have changed who is connected to whom. Now note that a map such as the one we had before would now not be an isomorphism because it doesn't somehow preserve the structure of the graph. Before we were sending an edge, 2 nodes connected by an edge to 2 nodes connected by an edge. Now we're sending 2 nodes connected by an edge to 2 nodes that are not connected by an edge, and vice versa. So that's the notion of graph isomorphism. Let's count the number of graphs on 3 vertices. There are 4 of them. You could have no edges, 1 edge, a path, or the complete graph. And if you think you're seeing a pattern here, think again. How many non-isomorphic graphs are there with 4 vertices? That's quiz 5. And the answer is, well, we need to list the graphs in such a way that we know we have all of them and we're not repeating any. One way to do that is to list the graphs in terms of the number of edges, because we know that 2 graphs with different numbers of edges cannot be isomorphic. There's only one graph with no edges. You just have the 4 vertices. And there's only one graph up to isomorphism with 1 edge. You just join to the nodes. There are 2 graphs up to isomorphism with exactly 2 edges. The edges could either join up to form a path, or they could be separated. There are 3 graphs with exactly 3 edges. You could have this star, you could have a path, or you could have the complete graph on 3 vertices with a node not connected to any of the others. But now the question arises, how do we know that this is all of them? Well, we could begin an enumeration. Consider, as we have been, the graphs with 4 vertices and 3 edges, and maximum degree equal to 3, 2, or 1, if possible. Maximum degree is the number of edges incident to a vertex. If you have a node with degree 3, that means there are 3 edges coming from it, but that takes up all the edges that we have, and so that would be this. If the maximum degree is 2, then these are the situations you could have. There must be a node with 2 edges coming from it, and then there's a 3rd edge somewhere else in the picture. That 3rd edge cannot be coming from this node because there's a maximum degree of 2. It could be coming from either one of these 2 nodes, let's say this one, but then it has to be going somewhere. It could be going here, or it could be going here. These are the graphs that we've already identified. It's also possible that the 3rd edge could come from the 4th point, but then it has to be going to somewhere else. Here, which we cannot have because then this node would have degree 3, or one of these other 2, and that's what we've already considered. And then the final scenario is where we have maximum degree 1, so we have an edge coming from here to somewhere else, and then neither node can have any more edges, and then we could join these 2, and then we could join the other remaining cases where we have maximum degree 1, so we know we have a vertex with degree 1, so there's an edge coming from it, say this one. And because the vertices have maximum degree 1, that means no more edges can come from either one of these points, but we've got 2 more edges to consider. That means an edge could come from one of the other 2 points to the other, but then there's no room for a 3rd edge. And it's clear that these are non-isomorphic graphs because they have different maximum degrees in this case, and here there's a node with degree 0, but not here. Now we could continue our taxonomy, except we note the following. If we have a graph and replace edges with non-edges and vice versa, we still have a graph. And in the case of 4 vertices, we can have at most 4 choose 2 or 6 edges. And when we replace edges with non-edges, we simply take 6 minus however many edges we have, and that will be the new number of edges. Therefore, once we have this list, we can just work backwards. And so we know there'll be one graph with 4 edges. And whenever 2 points are joined by an edge here, we don't join them by an edge here. So we get this picture, which we could also draw as this picture. And then over here, we would get this picture. And then finally, we get the complete graph with 6 edges here and 5 edges here for a total number of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the problem of graph isomorphism is to determine quickly if 2 graphs are isomorphic. I consider it to be the most interesting of the complexity questions of interest to computer scientists because the complexity status of the graph isomorphism problem is unknown. For those of you who know about such things, there's a class of problems that are considered to be computationally feasible and a class of problems that we believe are computationally difficult, and we don't know where graph isomorphism belongs. Note that we're not simply talking about whether or not you could recognize that two graphs are the same when you see drawings of them. It's a different question. However, we are now going to return to different drawings of a graph. A drawing of a graph where no two edges intersect in the middle is a planar drawing. We've seen that a graph can have planar drawings and non-planar drawings, but if it has a planar drawing, it is called a planar graph. For example, K4, the complete graph on 4 vertices, is a planar graph. We've seen planar drawings of it, but this happens to be a non-planar drawing of this planar graph. This brings us to quiz 6. This is the complete graph on 5 vertices. You can see that each node is connected to every other node, and this is clearly a non-planar drawing. The quiz question is K5 planar? Answer yes or no. And the answer is no, although, truth be told, you don't yet know the mathematics to show that it is non-planar. It seems as if, no matter how we draw it, edges will cross. The crossing number of a graph is the smallest number of crossings, in the middle of edges that is, for any drawing of the graph. This brings us to quiz 10. What is the crossing number of K5? The choices are 1, 2, 3, pi, infinity, and NP complete. And the answer is 1. Again, we don't yet have the mathematics for knowing that K5 is not planar, but here's a drawing of K5. Every node is connected to every other node, where we only have one crossing, and this seems like the best we can do. This brings us to quiz 11. What is the crossing number of a planar graph? Put your answer there, and the answer is 0. If it's a planar graph, you can draw a picture of it with no lines crossing. Now, we've drawn a picture of K5 with only one crossing, but there are infinitely many ways we could have tried to draw K5. How do we know that we cannot do better? And that's what we'll get to momentarily.